We've been talking about the oddness or evenness of a permutation, and the way to determine that is to calculate the number of reversed pairs of that permutation, of that x, if you like. Now, there's a much quicker way, much quicker. Like, you can do it in a few seconds instead of minutes trying to calculate all reverse pairs. And here's how you do it. So let's, I'll make that a 4. So here's an example of how to calculate whether a permutation is odd or even the quick way, right? Here's how you do it. So here's a permutation, just say x, and it's a member of the symmetric group of 4 objects, okay? So as usual, the upper row is just in numerical order, your 4 objects, you know, the IDs, if you like, of your 4 objects. And then, like, for this particular permutation, 1 becomes 2, 2 becomes 3, and so on. Okay, now here's the trick. You connect it, you draw a line, straight line, between the same numbers. So, like 1 and 1. So you draw this line, okay, and then 2, 2, draw the line. 3, 3, 4, 4. Now, there are 3 places, or intersections, or I just call them cross points, right, where they cross, here, here, and here. Now, just by counting those cross points, the number of them, I know immediately that this permutation x is odd. Huh? Why? Now, if that's true, it's, you know, this method is very, very convenient, very quick, right? You can just quickly just draw the lines, count the number of cross points or intersections, as Barnard calls them. I prefer cross points, or, well, same thing. Okay, so there's a theorem which says that the number of these cross points is actually equal to the number of reverse pairs. Now that's hugely convenient, right? Because remember, the number of reverse pairs, you use that to define whether a permutation is odd or even, right? You use that in the very definition of evenness and oddness. But if the number of reverse pairs is equal to the number of cross points, or intersections, same thing, using this method is just so much faster. It's so much more convenient. So I'll now prove theorem 42 that that's the case, that the number of reverse pairs equals the number of cross points. In fact, well, expressing this a slightly different way, for each reverse pair, there's 1 cross point. Okay? And if you have a pair that is not reversed, no cross point, no intersection. Okay? So it's strictly, it's really 1 to 1. So I will now try to prove this, and you can use this at great convenience because it's just hugely simpler and faster. It takes far less time. You just draw the lines, count the cross points, and add them up, and that will give you the evenness or oddness of your permutation. All right. Well, I'll give you one example to start with of the idea that if you have a reversed pair, you have a cross point or an intersection. And that's true of any pair. So so it's 1 to 1. If there's a reverse pair, there's a cross point. If the pair is not reversed, there's no cross point. Okay, and from that you can generalize to theorem 42. So the total number of cross points would be equal to the total number of reverse pairs. Okay, it's 1 to 1. Okay, so let's do a concrete example. Now here's a particular example of, so x belongs to S5, right? Now we've got 5 elements, 5 objects in our set that we're permuting, and this is one particular permutation. Okay, Now the trick of the proof involves rewriting these integers, these numbers here. Okay? Now remember the permutation is just these pairs, the pairings. 1 goes to 3, 2 goes to 5. That is the set of those pairings. That's the permutation. Now the actual ordering of these pairs, these vertical pairs, you can order them any way you like. Okay? But for obvious reasons, the tendency, the convention is just order them numerically. It's just tidier, easier. Okay. So, but the trick for the proof is rewrite these not in terms of just integers, but the x of something. What do I mean by that? Well, what is x? Sorry, the one here. Using this permutation, what is this one? Well, it's the permutation you get when you permute 4.
Avast virus database has been updated.
Thank you. So I use Avast as my antivirus. Okay. So in this permutation, 4 maps to 1. Okay. So 1 is the x of 4, the permutation of 4. So 1 is x of 4. So instead of writing 1 here, I can just rewrite it this way. It's the same thing, right? What is, if you permute 4, what do you get? Well, you get 1. Okay? So x of 4, that's just the permutation. It maps 4 to 1, right? So instead of 1 here, I just put x of 4. Now similarly, you'll do it quickly. 2, what's 2? Well, 2 is what you get when you map 3. Right? When you permute 3, you get 2. So for 2 here, I can write x of 3. Okay? When you permute 3, you get 2. If you permute that, you get 2. So I can instead of putting a 2 here, I can write x of 3. Okay? Hope you've got that now. I'll just quickly do some more. Or maybe do this one. So what's 4? Well, it's x of 5. If you permute 5, you get 4. So instead of this 4, just put x of 5 here, and so on. Alright? Now remember, this row here, this is equal to 1, that's equal to 2, that's equal to 3, and 4, 5, okay? This row here, the upper row, is in numerical order. Remember that, it's important in the proof. Okay, 1, 2, 3, 4, 5. And that is equal to 1, and that is equal to 2, and so on. So these 5 here, their value, the value, that's 1, that's 2, and so on. That upper row is in numerical order. 1, 2, 3, 4, 5. Right? Important to remember. Okay. Now let's translate, rewrite the second row, the lower row, and this 3 here, what is it? Well, it's x of 1. Right? If you permute the 1 using your x, if you permute 1, you get 3. Right? So instead of 3 here, I can put x of 1. So 3 is x of 1, or the other way around. If you permute 1, you get 3. So x of 1 is 3. Now 5. How do you get 5? Well, that's just x of 2. Right? If you permute 2, you get 5. So instead of 5 here, I can put x of 2, and similar logic. 2 is what? Well, that's just x of 3. So put, instead of 2, put that, and so on and so on. All right? Okay, so we have now rewritten this permutation in the x format, if you like. That equals that, that equals that, that equals that, and so on. It's just the same permutation, right? It's just rewritten in a different way. Here it's written just straight of integers, and here it's written as x of integers, where these x's, the x is your permutation, acting on one of these 5. All right? Okay, now let's just concentrate on any 2, I and j, any 2 of these, any 2 of your objects in your set. All right? And we'll consider 2 cases. Now these are pairs oh wait a minute, I better be careful. Not any two. The I has to be less than j, right? That was part of the definition of big N, you know, the number of reversed pairs. So I better put a quote around that. All right? It's not just any